counters whose the transmission, the clock goes from one flip flop to the next to the next. So, by the time the final flip flop gets its turn to change state, it is a while, and that is not acceptable, especially for high speed circuits. So, we also introduced the concept of synchronous counters. In synchronous counters, all the flip flops will get the clock at the same time. So, we will have to make sure that not all flip flops change states, only the required flip flops change state. For that, we need to know the count before and the count that is required next. We took an example of a 3-bit synchronous counter last time. In synchronous counter also we can have an up counter and down counter. What we saw in the last lecture, it was up counter. So, how does a down counter look? Synchronous down counter. So, let us say we have 3 bits again, 3 flip flops. By definition, synchronous counters, all of them, in all the flip flops, synchronous counter will get the clock at the same time. So, every time the clock is applied, goes from 0 to 1, clocks of all the flip flops go from 0 to 1. This is the clock. We will call it ABCS. We will have JK flip flops again. We will call this Q, and of course Q bar is also there. We will label them as ABC, call this QA, QB, QC, which means the count is ABC. Now, the down counter will have this following output. Start from 111, 110, 010, 001. After this again it will go back. Repeats. As long as the clock is applied, this sequence repeats. Now, one simple method is to look at what is the present C, what is the next C. We know in the D flip flop or JK flip flop, the truth table or the characteristic table is 0 0, Q remains as before, no change, 0 1, Q is 0, 1 0, Q is 1, 1 1, Q becomes toggle Q bar, that is if it is the next Q, previous Q. So, we will call it Q plus 1 or Q plus, this is Q bar before this Q, before this present Q, what is the previous Q, and that will be complemented. We will use that information here. If I use JK flip flops, I will call this JAKA, JBKB, JCKC. Now, the next state will be, this is the present state, next state will be, we will call it A plus B plus C plus. The present state is 1 1 1, next state will be 1 1 0. Present state is 1 1 0, next state is 1 0 1. One 0 1, next state will be 1 0 0. 1 0 0, the next state will be 0 1 1. 0 1 1, the next state will be 0 1 0. 0 1 0, next state will be 0 0 1. I am rewriting the table except one shift. 0 0 1, next state will be 0 0 0, and 0 0 0, the next state will be 1 1 1. To make it life simple, I will use D flip flops to start with, then we will make it JK. Simple understanding with D flip flops. So, I will call it DA, DB, DB, DC. Input D, input B, input C. D input of A, D input of B, D input of C. Now we know that in a D flip flop, present state and the next state, present state is 0 and D is 0, next state will be 0. Present state is 0, next state is 1, the Q plus will be 1. 1 0 0, 1 1 1. That means the D value is same as what we need next. These are identical. Or Q plus is D is Q plus. This is the characteristic equation. What is the input you should give? The input I should give is same as what I need as the next output. So now if I put DA, DB, DC, DA will be 1 because I will have to copy this table, that is all. 1 1 1 0 0 0 0 1. DB will be same as this, 1 0 0 1 1 0 0 1. C plus is DC will be 0 1 0 1 0 1 0 1. So what should I apply to DA will depend on what is the present value of ABC and what will make the DA, what DA will make the next state as 1. Present state of B is 1, what input of D will make the next state 1? Present state of C is 1, what input will make, what D input will make the next state 0. So that is this table. So I can draw 3 tables using corner map, 3 maps. The present ABC, and it will be for DC, it will be 0 1 0 1 0 1 0 1. Yes. So my DC should be same as C. This is C. This is B is 0, C is 1. DC is same as C. So if I get this C output into this DC, then we will have DB. This would be 1 0 0 1 1 0 0 1. This is this or this. This is QBE, TB will be this is DA, DC this is, DB will be B bar C bar or BC. And then the last map will be DA map. One 0 0 0 0 1 1 1 1 0 0 0 0 1. So this will be 1 DA value would be, this is A bar D bar, A bar B bar. This will be A bar C bar, and this should be ABC. So I have now 3 equations. DA is A bar B bar, A bar C bar, ABC, DB would be B bar C bar plus BC, DA would be this is DC, no? This is DA, DB, this is DC. DC would be C. So now I have C. I will have to make this DA as that equation. A bar B bar. I don't have to look for A bar because this is A, this is A bar. This is B, this is B bar. This is C, this is C bar. Now, so I have A bar, B bar, C bar available. A bar, B bar, A bar, C bar, right? A bar, C bar. And ABC. All of them join in OR gate, that will become my DA. D will be B bar, C bar, BC is B exclusive OR, exclusive NOR. So this is or you can put exclusive OR with an inverter. That is exclusive NOR, that is BC. This is nothing but C. So a synchronous counter, I can have a down counter, up counter the other day we saw 3-bit. I can now use any flip flop. D flip flop I chose because it is a simple reason. Next state of A will be same as DA. next state of B would be same as dB. Next state of C would be same as dC. Because of this is very simple to demonstrate to you that all I need to do is write the table, write the order in which you want the counting, and then write the next states for each one of them, and then you do the dA, dB, dC or whatever. So, I will give you a simple example using JK flip flop now. The same example can be done with JK flip flop. Using JK flip flop, we need to know the following. In D flip flop, the characteristic equation is very simple, because we said D is same as Q plus. What should be the next Q? That is the same as D. In JK flip flop, it is slightly different. We have Q, next Q plus, what will be J, what will be K. If Q is 0, Q plus also 0, I can make the next state of Q 0 either by making K is equal to 0, J is equal to 1, or making both of them 0. There are two ways in which I can make Q plus 0. The next state of Q can be 0. If I have the present state is 0, then I can have 0 0, or irrespective of what is the present state, next state will be 0 if I make K is equal to 0. Then we have 0 to 1 combination. 0 to 1 can be made either by toggling or by making J is equal to 1 and K is equal to 0, because when you make J is equal to 1, K is equal to 0, the next state will be 1 irrespective of what the previous state is, or I can have the previous state and toggle it to become the next state. Then if the present state is 1 and next state is 0, I will have K should be 0, so I can have 0 here and 1 here, or I can have 1 1. Finally, the present state is 1 and the next state is also 1. I can make it by giving both inputs 0 or by making J is equal to 1 and K is equal to 0. These are the 4 possibilities. Now, so we have now zero to 0, 0, wait a minute, if it is 0, present state is 0, next state is also 0, that can happen if I make J is equal, I am sorry, this is the other way, J is equal to 0 and K is equal to 1. So, this is, I can rewrite this, simplify as J has to be 0, K can be 1 or 0. In this state, J has to be 1, K can be 1 or 0. In this state, 1 0, 1 0 can happen if 1 1 or if K is equal to 1 and J is equal to 0. I have written the opposite. That means this has to be 1, this can be either 0 or 1. Now, the last one is this can be, do not care, this can be 0. So, a simplified characteristic table of JK flip flop is the present state and next state. Present state is 0, next state is 0. J can be 0, J has to be 0, K can be don't care. That means it can be either 0 or 1. Similarly, in the 0 1 state, the J has to be 1, Q can be 0 or 1. If the present state is 1 and next state is 0, J can be 0 or 1, but K has to be 1. And 1 1, the present state of J, if the present state is 1 and next state is also 1, J can be don't care, J has to be 0. I can use this table instead of the JK flip flop here, instead of the D flip flop here and do the same problem with JK flip flops, which we will do now. Again 3 states, I mean 3 flip flops, 8 states. We will first write the sequence. And use the JK flip flop instead of D flip flop. See how it comes. Again we are going to go for the present state ABC, next state A plus, B plus, C plus, again 3-bit down counter, 1 1 1, 1 1 0, 1 0 1, 1 0 0, 0 1 1, 0 1 0, 0 0 1, 0 0 0, after this it repeats. It's a 3-bit down counter. Now, as we saw already, I am doing this to make sure that the lines are still maintained, rows are maintained. So, the present state is 1 1 1, next state is 1 1 0, present state is 1 1 0, next state is 1 0 1, present state is 1 0 0, 1 0 1, next state is 1 0 0, present state is 1 0 0, next state is 0 1 1, 0 1 0, 1 1 1, 0 1 1, next state is 0 1 0. Zero 1 0, next state is 0 0 1, 0 0 1, next state is 0 0 0, and 0 0 0, next state is 1 1 1. Then it will go from this to this and back. Now instead of D flip flops, I am going to use JK flip flops. So I need JA, KA. What will I give as inputs to JK flip flop? 1 A, JB, KB. For second flip flop, I will call it JB, KB as the inputs. Third flip flop, I will call it JC, KC. To make sure that they stay in line, I will put these horizontal lines so that I do not deviate. Now, what is the circuit is going to look like? Circuit is going to look like this. JK flip flop 1, JK flip flop 2, JK flip flop 3. I am now calling this as JA, JB, KC. JB clock is applied for all the flip flops at the same time. Let us call this ABC, does not matter, you can call this A, this B, this C, does not matter what you want to call. You want to call this JA, QQ bar is AA bar. This is QQ bar, BB bar, C, QQ bar is CC bar. So, what we applied here is called JC, KC, JB, KB, JA, KA. The question is, what inputs to JC, KC will make C flip flop change from the present state to next state? This is the present state of JC, a QC, next state of QC is this. What inputs to JA, JC, KC will make this possible? Similarly, this is the present state of B, this is next state of B. What inputs to JB, KB will make this possible? Finally, this is A, present state, this is A, next state. What inputs to JA and KA will make this possible? For that, I will use this table QQ bar, QQ plus JK. So, we will do one at a time. We will start with JC. My reference I need here. So, instead of, so for present state JC to next state Z 1 0 it is. So, 1 0, present state 1 and next state 0, it is do not care 1. One zero, don't care 1. 0 1, 1 don't care. 1 0 again, 1 0 is don't care 1. 0 1, 0 1, 1 don't care. So, it will be repeating. This is 1 0 0 1, 1 0 0 1, 1 0 0 1. So, it will repeat, don't care 1, 1 don't care 1, 1 don't care. Is that right? 0 to 1 would be 1 don't care, 1 to 0 is don't care 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1. Now, next B, present state of B and next state of B, 1 1, 1 1 is don't care 0, 1 1. Then it is 1 0, 1 0 is don't care 1, 0 1, 1 don't care, oh I am sorry, 0 0 next, 0 0 is 0 don't care. Next is 0 0, 0 1, 0 1 is 1 don't care. This is 1 1, 1 1 is don't care 0, 1 0, don't care 1, 0 1, 1 don't care, 0 1, 0 0, I am sorry, 0 0 is 0 don't care, 0 1 is, please check your notes because seeing laterally there may be a parallax error, but does not matter, it means that I am telling you the concepts of how to do it. Then next 1 1 1 1 1 1, first 3, 1 1 is 0, do not care. Zero don't care, 0 don't care. Fourth is 1 to 0, 1 to 0 is don't care 1. Next is 0 0 0 0 0 0, 0 0 is 0 don't care. I think I left somewhere here. Sorry, first line is here 1 1 1 1 1 1, first 3 1 1 1 1 is 0 don't care, 1 1 is don't care 0, don't care 0, don't care 0. Fourth one is 1 0, 1 0 is don't care 1. Here next is 0 0 0 0 0 0, 0 0 is 0 don't care. Last entry is 0 to 1, 0 to 1 is 1 don't care. Now I have JA, KA, JB, KB, JC, KC listed. Again you have to go through the same procedure of drawing Carta maps and finding out JA, KA, JB, KB, etc. So instead of 3 maps you will have to draw 6 maps. JA map. Don't care, don't care, don't care, don't care. Okay, this is this order. This is 0, ABC 0 0 0, 0 0 1, 0 1 0, 0 1 1. So it is the reverse order now. So I will have to start from here and 1 1, and then it will become 1 0, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So it has to be reverse. That means I have to start from here 1, JA is 1, 0 0, don't care, don't care, don't care, don't care. This is JA. JA is 1. This is B bar C bar. KA. I have to start here again 0 0 0. So I will start from here. Don't care, don't care, don't care, don't care. And 1 don't care, don't care, don't care. 1 0 0 0. Again this is same thing. So JA is same as KA. B bar C bar. JB KB. We start from here, JB 1 0, don't care, 1 0, don't care. Nice. So this is JB is B bar, B is gone, C bar. KB map, again start from here because it is 0 0 0. So don't care 1 0, JB, KB, don't care 1 0, don't care 1 0, again same. JB and KB are same, C bar. Finally, JC, KC. Start from here again, JC is 1 don't care, 1 don't care, 1 don't care, 1 don't care. Now don't care can be treated as 1, so the entire thing is 0. So this is JC is 1. KC also we have 1 or don't cares. Looking at that you can write KC is also 1. Because it's only either 1 or don't care can be considered as 1, so everything is 1. So now my JC, KC are 1 1, JB, KB are C bar is here. And JA, KA are B bar, C bar. This is again a synchronous counter, down from 111 to 000 and repeat. This is using JK flip flops. Now I think what I did earlier with D flip flops also I must have started here. I should have considered here. So you can make your correction. Whatever DA, DB, DC I drew, you should redo the corner maps with this as the starting point, not this. Earlier I must have, I think I have done this starting from here. So it is a reverse of what is happened. So this is the 0 0 1 0 0 0 0 0 1 0 1 0 0 1 1. So you can do that. This is next state. So I can also do DA, DB, DBC one more time to make it clear. DA same as A plus. This is A plus. We start from here 1 0 0 0. You have to write, start from here 1 0 0 0 0 1 1 1. This is my DA. DB would be, this is nothing but that is, this is A C, A, B, A bar, B bar, C bar. This sort of an inverse of what I wrote earlier, because there I considered this as the starting, I should have considered this as the starting. So, correct the notes, please correct dA, dB, dC I do earlier using corner maps. I should have started from here instead of here. There I started here and came here, that is wrong. So, it start from here and go back, and so the values of dA, dB, dC will be different. Actually, it is a complement. Whatever you had, it is a dual or the complement. So, dB, dC, dC, same thing, dB bar So, again you start from here 1001, 1001. This should have been same because there also we have the same thing. So, this should be dB is B plus, which is B bar, B, C bar. DC would be again starting from here, it is alternate 1 0 1 0 1 0 1 0. So, this is A is gone, C bar again, TC 1 0 1 0 1 0 1 0 1 0 0 1 0 1 0. dB is 1 0 0 1 1 0 0 1, both are same. How come? 1 0 1 0 1 0 1 0 1 0 1 0 1 0. There is also C plus, C bar. Let me check this one more time, must be right, but still. 1 0 1 0 1 0 1 0, that is right. So, that is C bar. Earlier map dB 1 0 0 1 1 0 0 1, yeah, it happens to be same. So, what I am saying is earlier we did this problem with D flip flops. There I drew 3 maps dA, dB, dC maps, but I considered this as the starting point and this is the ending point 0 to 7, but this should be other way. This is 0 to this 7. So, whatever map I drew is now the inverse, these maps. So, naturally these values also will be inverse, complement of the earlier thing. So, this is how you do any design of synchronous circuits, whether it is up counter, down counter or any other counter. I can also have a counter in which we do not have sequential. We can go non-sequential. So, non-sequential counters also is done in, because that depends on the states. You go from state to state, sometimes the states are not in sequence. So, we will call it non-sequential counter. What do we mean by non-sequential counters? A counter which does not count in sequence, out of sequence. We need this some places. In suppose you want a memory access, non-sequential counters. Suppose you go from memory access from one place to next place, jump back, jump forward. So, the memory address has to be non-sequential. That is one example. There are several examples. You supposing you are in an office where papers are being processed. Depending on the simplicity of the paper, somebody may be called earlier than you, even though you went and gave your paper earlier, somebody may be called earlier because that person's papers are straightforward and your paper may be a slightly complicated processing is involved. So, even though you have given the paper first, somebody else who gave the paper later would be called. This is another place. So, when they put the display, the sequence need not be always 0 0 0 to 0 0 1 to 0 0. Depending on whose paper is ready for processing, that count will come on the display. That is one example again. So, what do we mean by that? For example, we will take a counter which goes from binary 2 to 3 to 5, 7, 6 and back to 2. So, I have counts 2, 3, 5, 7, 6. I need a 3-bit counter because maximum state is, the largest state is 0 0 1 1 1. So, I will call this again ABC present states. Now, I am doing it sequentially. When I write the present states, earlier because the down counter I started with 1 1 1 and went back to 0 0 0, that is why we had to do the mapping from bottom to top. In JK we did it, D we did not do it, but then I corrected it now. Whereas any other thing you can do it in a sequential manner, the present state 1 0 0, 1 0 1, 1 1 0, 1 1 1. The next state would be, there is no 0 0 state, so there is no question of next state. You call A plus B plus C plus. This A plus B plus C plus only just tell you not confuse with this A B C. I can't have two things as A. A plus means the next state, that is all. Plus stands for next state, not for anything else. So, you have to understand it clearly. So, present state 0 0 0 does not produce a next state, so I put don't cares. Present state 0 0 1 also does not produce a next state. Present state 0 1 0 will produce a next state 0 1 1. Present state 0 1 1 will produce a next state 1 0 1. Present state 1 0 0 does not have a next state. Present state 1 0 1 will produce a next state 1 1 1. Present state 1 1 0 will produce a next state of 0 1 0. Present state 1 1 1 will produce a next state of 0 1 1. So, this is the next states correspond to each present state. Now, I can do account this, and again because we are going to use corner maps and simplify them, it does not matter at all. We know the behavior of D flip flop, we know the behavior of JK flip flop, you can use any flip flop. I will use D flip flop to make it simple. So, I will have to draw 3 maps, DA map, A plus will be DA. If I have to get a nested A plus, what I should give to A? D flip flop input D, that is called DA map. DA map is nothing but the inputs I need to give to A flip flop, D of the A flip flop, so that I can get the next A plus state properly. So, again I make it 0 0 0, then DB will be the inputs I need to give to flip flop B in order to get the next B plus state, and DC will be the inputs I need to give to C flip flop, D of the C flip flop, so that the next state will be what is required for C plus. Now, let us look at A. This is don't care, 0 1, don't care 1, 0 0. DB don't care, 1 0, 0 don't care, I am sorry, don't care 1 0, don't care 1 1 1. DC don't care 1 1, don't care 1 0 1. Now, how do you read this map? Very simple. This one can be combined with this 3 don't cares. This one can be combined with this don't care. Now, this should be A is gone, B is gone, I mean C is gone, it's B bar plus A bar C. This is C bar, B is gone, A is gone, and this is A. This is A bar plus A is gone, C is gone, I mean B is gone, it is C. So, I need 3 flip flops, DA, DB, DC, this is DA, DB, DC, this is Q bar, I will call this AB, A bar, BB bar, CC, I am sorry. Clock is all same. Same clock is applied to all the flip flops. DA is B bar plus see A bar, B bar, C bar available. So, no inversion is required. So, it is B bar or A bar C. This is going to be DA. DB, C bar or A. This is A bar or C. That is all, circuit is ready. So, any arbitrary sequence I can get. So, synchronous counter is so beautiful. First of all, there is no problem of propagation delay. The only propagation delay is an individual flip flop. After you apply the clock on the input, there is a certain time lapse between A bar occurs, at the same time B bar occurs, C bar occurs. The combinational logic is not very huge. If the combination logic is very huge, then the delay will be more. We will assume that normally these combination logics are very simple, 2 gates, 1 gate, 1 gate. So, it is a small amount of delay and clock is applied. After the clock is applied, this will be ready even before the clock comes because A bar, B bar, A bar, B bar, C bar are available already. So, the delay of the combination logic can be ignored or need not be taken into account because this DA, DB, DC are available even before the clock comes. So, these are stabilized. I do not need to take into account the delay of this combination logic, this and this. All I need to do is after the clock is applied, how long does it take for A and A bar to come, B and B bar to come, C and C. It is a small amount of delay. Irrespective of how many flip flops you have in your circuit, the delay is very, very small. That is a major advantage compared to the ripple counter. Second thing, I can design any counter with an up counter, down counter. I can just write the present state, next state and corresponding values of DA, DB, DC or QA, QB, QC. I mean DA, DB, DC or JA, KA, JB, KB, JC, KC by using the characteristics tables. If it is a D flip flop, next state is same as the present input. The combination, this DA is same as A plus. So, the next state is same as the input present input. Here next state is same as the present input to B. Next state is, that is one thing. JK flip flop is slightly more complicated, but it is very easy because we found large number of don't care states in that. So, you can either use a JK flip flop or a D flip flop and get whatever count you want, up counter, down counter, arbitrary counter, arbitrary counter or arbitrary sequence counter or non-sequential counter. So, that is a major improvement over the ripple counter where we had to decide the next state by taking all the inputs of the present state and triggering the clear or the preset state using a combination logic gate. All those things are not required in this. This is a beautiful thing. Supposing you want a decade counter, what do? You take a 16-bit, 4-bit counter, 16 states, 0, 0, 0, 0 to 1, 1, 1, 1. After 1, 0, 0, 1, after 9, you want to go back to 0, 0, 0. This is given as an exercise to you. We can now do this problem. I want a counter, synchronous counter for counting from 0 to 9. What does it mean? I have 4 states, I mean 4 bits A, B, C, D, starting from 0, 0, 0, 0, all the way to 1, 1, 1, 1, but I want after 0, 1, 0, 0, 0, 1, 0, 0, 1, this is 9, this is 0, this is 9, this is 15. I don't want 15, I want only 9, 0 to 9 just one states. After this you repeat. What do? I write the next states. That is 0, 0, 0, 0, next state is 0, 0, 0, 1, next present state is 0, 0, 0, 1, next state is 0, 0, 1, 0, so forth. Present state is 1, 0, 0, 1, next state will be 0, 0, 0, 0, because I want this to repeat after 9, count 9 or after 10 counts. What do you do for the rest of this? The rest of this is don't care, because they will not occur. Your decade counter will not go beyond 9. So, if 10, 11, 12, 13, 14, 15 come, you do not have to worry because those things are not going to come, so you can put all don't care. Now, I can draw corner map for A, B, C, D, and then write a DA, DB, DC, DD, 4 equations, and then draw 4 flip flops with all the clocks same time, A bar, B bar, C bar, D bar, and DA value, DB value, DC value, DD value. So, this is one shot, in one single shot. We have covered a lot of material because we can now design up counter, down counter, non-sequential counter, decade counter, whatever counter you want, synchronous counter. So easy to do, and that is why most of the time we use synchronous counters. Ripple counters are not used very much. Are there any questions? Now, what next? After the counter, we use, if there are no questions, I will continue.
Sir, this is we are using flip flop. When I start the circuit, then it will be arbitrary value. It will start from 0 or it will be start from arbitrary values, sir.
Arbitrary, does not matter.
Arbitrary.
It starts arbitrarily because you can't start it at 0, 0 unless you reset it to 0, 0, 0. So, it starts arbitrarily anywhere, but then in sequence will count back to that.
It starts from 2, then it will come back 0, 0.
No, if it is a 0, 0, 0 to 1, 1, 1, 3-bit counter, it can start in 1, 1, 1, or it can start in 1, 0, 1, it can start anywhere, but first count cycle you should not take it. From the next
Okay, sir.
count cycle only it will be useful to you. Arbitrary only it will start. Unless you make it a
Okay.
point to use a clear signal to start with, before you get the counter clock, you can make a preset and clear signals and make it 000 and then apply the clock, then it will follow 000 to 111. That is arbitrary anywhere. Any system, take a control system, there will be an arbitrary point and then you will have to get back to the normal. So, this is a common law anywhere. Okay?
Okay, okay, sir. Sir, I have another question. We are considering 101 is this is not in the counter sequence, then we are considering don't care. All are don't care.
Because those things when they occur, because they are not going to occur, what is the next step we do not have to consider. It is not in the
Uh,
sequence.
okay, okay.
Why do you mark don't care means, take this example of decade counter. After 9, 10, 11, 12, 13, 14, 15 I make don't care. Because I am sure that if I count the design properly, if I design the counter properly, after 1001 it is going to go back to 0000. So there is no question of 10, 11, 12, 13, 14, 15 occurring at all. That is why I put don't cares. I can always make,
Okay.
I can also make
In
all of them
between,
zeros. I will make, if 10 comes make it 0, 11 comes go to 0, 12 comes go to 0. I can make my life more miserable and your life also. I can do this because by chance some stray arbitrary thing occurs here, I will redirect it to this. I will redirect to this. Okay? That is also possible. That is extra
this
hardware.
is fine. This is fine. In between fifth value,
Huh.
then we can put don't care. In accidentally a fifth comes, then it will give arbitrary value. That is unnecessary count. It will count.
I don't understand your question. Repeat it.
What I am saying is, fifth count is not needed in our counter sequence. Then
Okay.
we put don't care in all the values.
Uh-huh.
Okay. We are considering that in any one of the circuit, then it will give accidentally fifth count is comes accident. I
Yeah.
am meaning accidentally. It is not in sequence. Then it will give arbitrary value. Correct?
Yes. But what you should do is, in that case, whenever a non-sequence comes, supposing I have a counter, now 1, 4, 5 are not occurring, right? 1, 4
Yes.
not occurring. Supposing 0001 comes, because when you switch on, I said arbitrarily it will start anywhere, it can start in 001. So that is why you should check. After you do the design, I will give these values which are not in the thing and make sure it will go to one of the allowed states. These are called illegal states. After you design your circuit, you give values of 001 to DA, DB, DC and see what happens. If it goes to one of the legal states, you are fine. If it does not, if it goes from here 1 to 4, suppose it goes from this will form a loop. It's an illegal loop. For that, what you should do is, I will deliberately put a 4 in the count sequence and put 000. Even though it is not required, I will insert 4 in my count sequence, put the next state as 0 0 0. I will make sure one of these states next state is 0 0 0. If I make it, then it will fall into legal states. This I did not mention because I was just introducing circuits to you today. So, if you have a state which is not in the list, these are called illegal states, not because they are illegal, but they are not required for us. So, they do not occur, and you have to check after the design of the counter, you have to check each of the illegal states, give the inputs corresponding to the illegal states, see what the next state is. If the next state happens to be one of the legal states, you are fine. Check for 1, check for 4, check for 5. If all the 3 states lead you to one of the, not necessarily 0 0 0. If one of the legal states, you are happy. If they fall into a loop, even if 1 does not go to the given state, 1 will fall 4, 4 will have to go to 0 0 0. It is enough if one of these goes to one of the defined states. In that case, if it is not falling, if it is going into the loop, then I will introduce, even though 4 is not in my sequence, I will introduce 4 and put as 0 0 0 and then design my circuit. Okay?
Okay, sir.
Very good. Now what next? We have seen counters, all types of counters. We saw reset, clear, preset, clear, everything. Where are counters used? Many places. You can count people, as I said, count cars. Counters are used in banks, everywhere. Elevators, lifts go from, if it's a 9-story building, it goes from 0 to 9 and comes back to 0. Now, the use of counters, another place is called registers. Registers are very commonly used in digital design. What is a register? Register is nothing but a bunch of flip-flops. So 4-bit register. What I do in a 4-bit register is I use 4D1 at the clock cycle. After the clock is applied, it becomes 1001. I can read it as 1001. If I change the value, the new values will come. So before you change it, you need 2 things. One is a clear. I may want to clear the register to 0000 to start with. Clear. Or I also have a load signal. Load signal loads the DA, DB, DC, DD values to the registers DA, DB, DC, DD, flip-flops DA, DB, DC, DD, which are available outside output. A clear signal will make all values of flip-flops 0, 0, 0, 0. So normally a register will consist of a set of flip-flops clocked by a common clock with 2 input signals called input signal DA, DB, DC, DD, of course QA, QB, QC, QD being the output. 2 common input signals, one is called the load, the other is called clear. The clear signal is also called sometimes reset. When you clear or reset it, the flip-flops will assume value 0, 0, 0, 0. Then I can load it with a new value. I can keep it, or if I want to put a new value, I can load it with another value. Any value I can load. But as long as the clock comes, the clock will keep it inside. It is available here. If you don't change the inputs, however many times the clock comes, the input will remain the same. If I want to change the inputs or change the content of the register, I should give a new load signal. I will put a new values of 1 1 0 0 and again give the load signal. Load and reset are generally non-synchronous. They can be given any time, not necessarily the clock. Depends. Certain registers will have a load has to be given along with the clock, clear has to be given. But generally many registers, most of the registers, load and clear are signals which are asynchronous. What do you mean by asynchronous? They can be given any time irrespective of when the clock comes, usually. Now from here you move to shift registers. A shift register is nothing but same bunch of registers I have a D, Q of one flip flop goes to the D of the next flip flop and so forth. So I can clock it all at the same time. So when I clock it, whatever is this D goes here and whatever is the previous Q goes here. Now after one clock cycle, this Q will go here. So let us start with 1 1 0 0. After clock 1, this becomes 0 1 0 0 1 1 0. After second clock, it becomes, depends on what you give here. Supposing you give 0 afterwards, unless you give a new value to D every time, whatever value you gave, it will disappear. So this will go from here to here, and this goes from here to here, this goes from here to here, this goes from here to here. This is assuming after given the first value, I am not giving any more values. If I keep giving the new values, then it will also change. Or sometimes this Q is put back here, it's called recirculating. Recirculating shift registers means it is 1 1 0 0, next cycle it becomes 1 1 0, this 0 will go here. Next cycle it becomes 0 1 1, this 1 will go here. Then next cycle it will become 0 1 1 will become 1, this 1 will go here, and then next cycle, I lost a 0 somewhere. Second time also it will be 0. 1 0, so this will be 1 1 0 0, which is the starting value. So if you don't want to lose the data, I can recirculate it so that it remains. This is called recirculating shift registers. We will see some more of shift registers next lecture. Today I will stop here. I told you what a register is, and register is nothing but a bunch of flip flops with common clock, inputs and corresponding outputs, can be cleared. All the flip flops can be cleared at the same time. All the flip flops can be loaded at the same time with the new values you give, and then they will be retained here as long as the clock is there if you don't change the inputs. And when you do this in a sequential manner, from one flip flop to the next flip flop it goes Q connected to D, Q connected to D, Q connected to D, and then this Q back to D. This shift register which keeps circulating whatever data you put. We will see some more of shift register in next lecture. I am stopping here. Are there any questions? Kannan?
Yes, sir.
I am stopping here. You can unmute for a minute.
All right. Okay, you want to take any questions or shall I close?
No, if he has any questions, I will take.
Sir, register in microprocessor. These
Huh?
registers are used. Register, we
Don't
are
use
speaking
words.
register.
Don't use words you did not use. Why are you introducing microprocessor here?
I am asking, these registers are used in microprocessor.
It can be used anywhere.
Okay,
It is used in
okay.
a calculator. Yeah, microprocessor also uses it. What is your question? Now ask me. What is your question?
My question is, my microprocessor has bunch of register. Bunch of register means A, B, C, D, T, H, stack register. These kinds of registers are available. These
Yeah,
registers are access. Uh, these registers have the same clock or different clock.
you are totally confusing me because microprocessor has a single clock. And
Yes,
inside there may be several clocks because there may be division of clocks. So whether
okay,
A, B, C will be using the same clocks or not, it depends on the type of microprocessor. Usually they are the same. Okay?
okay, okay,
And
sir.
you always
Register used. These registers are used. That is enough. Register has address or not. You are accessing register means every register has address.
yeah, you are again going to a microprocessor. Yes, registers have addresses. In memory, why do
Okay.
you want to go to microprocessor? Memory has address. What is the
Yes,
memory?
yes.
Memory has
RAM.
bunch of registers. Each set of registers has an address. Suppose I put the address value in 000, it will remain in 000. When I want, I can put an address 000, I will get it back. Okay?
Okay.
I will talk more
Okay.
about
Long
registers.
memory.
I will talk more about
RA
registers.
in memory.
I will talk more about registers next class. I told you.
Okay.
Wait.
Okay, sir. Okay.
Okay.
And I have another question. Register based on clock and load is here. Clock is changing continuously.
Yeah.
When clock is changed, then input change. Accidentally. That will make problem.
If this is the bunch of flip flops and I am
Okay.
clocking it, as long as I don't change the value, I have loaded it once. I have loaded
Okay.
and 1001. The clock keeps coming, but doesn't matter because I am not putting a new values here. If I put new values here, I have to again apply load signal, then it will change and then every clock it will be there. So that is why I wrote this as asynchronous clock. Anytime I want to load it, I can give it load signal, new values I
As
can
well as
put, get it.
load is asynchronous. Okay. Clock is when the clock is high, on the time input is changed, then what will happen?
What?
Clock is high. Clock is high, input is changing. That is, I am giving the value changing. Then what will happen?
What is this? What is the symbol?
Positive edge trigger.
Edge triggered. So only when the edge is there, we talked about setup time, hold time.
Yes,
Nothing,
yes.
nothing will happen
Nothing will happen. Okay,
because
okay.
clock is edge triggered. Okay?
Oh, okay. Edge trigger means on the particular time only this will sense. Okay.
Before
Particular time on that particular time input change. What will happen?
nothing will happen, sir. What are you talking about? You see, I need to put 1001 before the clock using the setup time.
Okay, okay.
Before the setup time, I give it, and then the new values will go to the clock. New
Oh,
values will
okay,
come
okay.
here. Load is to give new values here and then change it every time. Okay?
Okay.
Uh,
Mm. Okay, sir. And I have the flip flop has the setup times plus hold time and flip flop that latency. These are summed. They have give frequency. That is the frequency we are using.
yeah. Maximum frequency.
Uh,
That is
maximum. Every memory we are considering ROM is in market, different ROM is available. Their frequency differs by that value.
ROM or RAM, what are you talking about?
RAM.
RAM is called RAM, first of all. You should not say ROM. Okay. Why is this RAM,
RAM.
RAM connected to this? RAM is a
Because
register.
because ROM speed is based on the frequency also. Flip-flop is the basic component of memory, so its frequency is common to RAM. So
RAM.
this
RAM. Say it RAM. RAM.
RAM,
Why
correct?
don't you trying it saying RAM? RAM.
There is some
Okay. What is that? Tell me.
every memory we are considering main memory. There is some frequency, speed is there. That frequency is based on the flip-flop frequency.
Yeah, which is same as for all the flip-flops.
As well as
once you say RAM, they will say this is the maximum frequency at which you can operate. That is considering flip-flop speed, which is considering setup time and the flip-flop delay. Okay?
Okay.
All.
That frequency is used to common. Okay. Every address has different clock as well as.
Every address has different clock.
Because it's changing same time means sometimes it will happen accidental change.
There is only one clock. You only read one flip-flop at a time, one register at a time.
That I am meaning. That I am meaning. What I meaning? RAM has 2 power 10 address means 2 power 10 register.
Yes.
2 power 10 register has common clock means when I change the clock, when the clock is high, I want to change only one register. Clock is common, then the data change, whole data will change.
You have to address it. Address, register and the clock together will only change. You can't just arbitrarily change anything you like. Address has to be given.
Address given, then the
That
address
that location only will change.
Okay.
So the same clock will work.
Okay, sir. Thank you.
You are introducing a lot of things which is not covered in this course. Because the other persons who see these lectures will get confused. I don't mind answering you. You are asking a lot of questions, I have no problem. But the people who listen to me or people who see my video will get totally confused because they are not familiar with all the terms you are telling. This is the first course in digital. What you are talking about is microprocessor, RAM design, ROM design, this design. I don't mind, you send me emails. Okay?
Okay, sir.
Because whenever you are asking questions outside from what I covered, you should send me emails because otherwise the students will find it extremely confusing to the last 10 minutes of every lecture they get totally confused because we are discussing something like a higher level philosophy and very difficult for people who are not into this to understand what we are talking. I don't mind answering you, don't mistake me. I don't mind answering you, or you come 10 minutes early and ask me questions before my thing gets recorded.
Okay, sir.
Once it gets recorded, I would not like to deviate from what I have been doing. Okay? That is not because I am like that. It is because I do, in the interest of other students who are likely to see these videos. Do you understand me, sir?
Yes, I understand, sir. My email ID is Srini.
No. You ask me. No. You come 10 minutes earlier and ask me.
Okay, sir. Thank you.
Because email you will ask something, I have to write 2 pages. I have no time. You come 10-15 minutes early every day, ask me any number of questions, bombard me. Okay?
Okay, sir.
Thank you.